Hi, welcome back to es346 Basic Thermodynamics. This is module 7.8 on isentropic efficiency. The section in the textbook is section 7.12. And the two learning outcomes for this module, at the end, you'll be able to formulate an equation describing the isentropic efficiency for a steady flow device, and you'll be able to calculate the isentropic efficiency of steady flow devices. So first, let's kind of think about what we're trying to do here. Imagine that I have some device. It could be a compressor or a turbine or a nozzle or anything, and I think it's not very efficient. In fact, I'm considering replacing it with something that is supposedly more efficient. And the question is, well, how much more efficient is it? So let's consider what's going on here. I've got some device where I have material coming in with some entropy S1, and if it's not very efficient, it's coming out with an entropy S2, which is greater than S1. Because we know that things that are less efficient, they're irreversible, they're generating some entropy. Now, if I was to have a more efficient device, S1, the entropy that's coming out of that, if it's truly more efficient, would have maybe an entropy S3, which is also less than S2 because it's a more efficient device. In fact, the most efficient device I could have would say that the outlet there would just be equal to S1. It's generating no entropy. I can't get any more efficient than that because otherwise I'd be destroying entropy, and we know we can't do that. So what would be a good metric for measuring the efficiency of devices like this is to go ahead and compare how much entropy is actually being generated. So a good way to do this is to go ahead and look at a property plot that we haven't seen yet before, and this is called a Moyer diagram. Moyer, and it's H versus S. So I have two intensive properties, the enthalpy and the entropy. And you look on here, there's like where the saturation curve is. So it's sort of similar like before. You have sort of this little hill. Over here you have vapors. Over there you have compressed liquids. And we've got our saturated liquids there and our saturated vapors on that point, and superheated vapors out in this region. The thing I want to point out is lines of constant pressure on here. So for example, this line right here is 50 psia, and then this is 10 psia, so a lower pressure. And so the important thing is that that's a high pressure and this is a low pressure, is that the pressures go from the upper right to the lower left. Now consider a turbine that maybe has an inlet at that point there, and as the material goes through the turbine, it's going to be dropping in enthalpy and maybe generating some entropy because it's somewhat inefficient as you going to the right there. Now the best that any turbine could do would be one that doesn't generate any entropy and goes straight down in outlets right there. And so it would actually have an outlet that's a slightly lower enthalpy. So let's kind of look at this, clean this up on a little diagram a little bit more. So again, I got an HS, and I'm going to go ahead and draw two isobars like this. Call that pH, call this PL. And let's consider a turbine. So I've got material coming through like this, coming from some H1 and an outlet of H2, and it's going to be generating some work. And so how much work does this generate? Well, the amount of work that it's generating is going to be m dot H1 minus H2 from a first law energy balance. Now, let's go back onto this HS diagram and consider that maybe this is the inlet enthalpy right there. Call that H1. Now as it goes through my turbine, maybe it outlets at this point here. And I'm going to go ahead and call that H2. Now I realize it generated some entropy because it went somewhat to the right. If it was a more efficient turbine operating between the same pressures, it would actually outlet down here because it would generate no entropy, it would be isentropic. And so that point would be H2. I'm going to call it H2S, meaning that would be a point that generates no entropy. And I'll call this one H2A for actual. So this is my actual outlet enthalpy. And this is a hypothetical turbine that's perfect. So if I look from this equation here, the amount of work is the difference between H1 and H2. And so here's my actual turbine. There's my work. I'll call it WA for the actual work being generated. And if the turbine was perfect, this would be I'll call WS, and that was the one that's generating no entropy. So we could go ahead and define an efficiency, which is the actual work being generated over the isentropic work being generated. And that number right there is going to be between 0 and 1. If it's perfect, it's going to be equal to 1, and it could be 0. I could just go ahead and have a turbine that's generating no power at all, and it's just dropping down the pressure there. So this is what's called the isentropic efficiency. Okay, let's go ahead and do a numeric example. So here I want to calculate the efficiency of this steam turbine, and given these inlet conditions and given these outlet conditions. So remember, the efficiency is the actual work being generated over the isentropic work, which is equal to H1 minus H2 actual over H1 minus H2S, or H2 isentropic. So the inlet enthalpy, I can get H1. This is a superheated vapor, so I can just look that right up on the superheated tables. And H1 is equal to 3399.5 kilojoules per kilogram. And so then this point right out here, this is H2 actual. And so I can go ahead and look that up. And that's also on the superheated tables. So H2 actual is equal to 2682.4 kilojoules per kilogram. So I've got three of the 4 terms that I need in terms of my efficiency equation. But what I need to do now is I need to find out H2S. Remember, this is the enthalpy of the theoretical turbine that generates no entropy at all. And that one means that the entropy that goes in is going to be equal to S2. So I can maybe call it S2S is equal to S1. There's an entropy down there, and it's going to have a different enthalpy associated with that. So what I need to do is I need to find out S1. So I'm going to return to that superheated table with my inlet conditions and look up S1. That is 6.7266 kilojoules per kilogram Kelvin. And now what I want to do is I want to find out what would be the enthalpy with that same entropy and this pressure here. Right? So what I'm doing is I'm finding H2S, and the pair that I'm using is S1 and P2. Those two intensive variables. So I'm going to go to the pressure table and look, and what I realize is that S1, this value here, is less than Sg at 50 kPa. What that means is that the isentropic turbine, what would be coming out would be a mixture of what's called wet steam. So what I need to do now is find out what is the outlet quality. So X2, I'll call it X2S. Just remember, I'm talking about that hypothetical point. And this is going to be S minus SF over SFG. I'm using the 50 kPa line here now. So I'll put some numbers in here. 6.7266, that was S1. And then 1.0912, that's SF. And SFG is 6.5019. And that gives me X2S is equal to 0.867. So there's the quality. Remember, this is the hypothetical turbine. And now I can use that to go ahead and find H2S. Let's give ourselves a new piece of paper here. And just to remind ourselves of our efficiency equation, we have H1 minus H2 actual, H1 minus H2S. And so I'm finding H2S at this point, and this is going to be HF plus X. This would be that 2S value I just found, HFG. So we'll put some numbers in here. This is 340.54. Remember, still using the outlet pressure here, 50 kPa, plus 0.867, that value of quality I just calculated, and then 2304.7 is HFG. So that gives me 2338.7. So that's H2S. Now I've got all my values. You can go and plug those into the efficiency equation. So 3399.5 minus 2682.4. So H1 minus H2 actual, 3399.5 minus the one I just calculated here at 2338.7. And that comes out to 0.675, or an efficiency that is 67.5% efficient. So not all that great. All right, let's look at some other devices. And so what I'm going to look at now are compressors. So now I have a compressor. This has a work requirement to go in. And let's think about this on how this would look on a Moyer diagram. So I'm going to go ahead and draw two constant pressure lines. This will be P low and this will be P high. And a compressor, we take a material from some low pressure like that, and maybe at outlets right there. So this right here I'll call H1, the inlet enthalpy. And then this point right out here, H2 actual, so H2 the actual outlet enthalpy. And we know from our first law the work for a compressor is going to be equal to H2 minus H1, in this case H2 actual for this turbine. So this right here represents the actual work that goes into the compressor. Now if it was a perfect one, it would go straight up and it would output right there. So that would be H2S. And that right there, called WS, that's the isentropic work requirement, and that's less than the actual. So that makes sense. We can define our efficiency now, which is going to be the work requirement, the isentropic over the actual. So it's sort of flipped from what we had for the turbine, but again, this value will be between 0 and 1. Let's do another numeric example. Now I've got a compressor and I'm using air. I've got these inlet conditions and these outlet conditions, and we want to go ahead and find out what our efficiency is. Let's write our efficiency equation. That will be H2S minus H1 over H2 actual minus H1. And I've got air, that's an ideal gas, so I can actually replace my delta H with Cp delta T. So that will be Cp T2S minus T1 over Cp T2 actual minus T1. And those CP's cancel. So now I've got this efficiency equation in terms of temperatures. And I'm given a T1 at 25, I'm given T2 at 350. So actually, all I need to do now is find T2S. So what would be the outlet temperature of an isentropic compressor? And I can get that if you remember this expression. T2 over T1 is P2 over P1 to the K minus 1 over K. That's isentropic compression. So I can use that to solve for T2S. This would be the outlet if it had been compressed isentropically. So it's going to be T2 is equal to 298. That's T1. I've got to do this in absolute because these equations only work with absolute temperature. And then P2 is going to be 1000 over 100. And then that's going to go to the 0.4 over 1.4 is my K value. And that is 575 Kelvin, or if I convert that back to Celsius, 302 degrees Celsius. So it's less than this outlet temperature, which makes sense because if I'm putting less work in, I'm not heating it up as much due to friction and inefficiencies within the turbine. Let's go ahead and calculate our efficiency now. We've got 302, which is the ideal outlet temperature, minus the inlet, which was 25. I'm doing this all in degrees Celsius now. And this will be 350 minus 25. And that gives me an efficiency of 0.85, which is 85% efficient. All right, we're going to just briefly talk about one more device here. We're going to talk about a nozzle. And so let me draw a nozzle. I have material coming through like that. It has an inlet enthalpy H1, an outlet enthalpy H2, and we have an inlet kinetic energy 1, an outlet kinetic energy 2. And recall, a nozzle converts enthalpy into kinetic energy. And let's draw a couple isobars on a Moliere diagram, P low to P high. And think about what it would look like for our nozzle. So we would have some inlet enthalpy there, and if it's a not perfect nozzle, might have outlet conditions there. So here's H1, and there's H2 actual. And so what the nozzle does is it takes changes in enthalpy, converts them into changes in kinetic energy. So what I realize is that this distance right here, H1 minus 2 actual, is delta KE actual. If I had a perfect nozzle that generated no entropy, its outlet would be down here, H2S. And so that distance right there would be delta KE isentropic, which is larger than the actual. So delta KE isentropic would be greater than delta KE of the actual one. So A perfect nozzle would go ahead and actually end up with a larger change in kinetic energy. Now you may be wondering, I mean, how can a nozzle be generating entropy? What's going on with there? And it turns out that there's only one shape of a nozzle that generates no entropy. It's an isentropic nozzle shape. Delta S would be 0 as you move through it. And I show it here for actually a supersonic nozzle, which we'll look at more in Chapter 7. But this is what the shape of the nozzle is. It's not straight at all. And this nozzle goes down, and then actually if it's supersonic, so it actually goes up to something greater than Mach 1, so Mach will be greater than 1 at the outlet over here, it actually gets a little bit larger. But this shaped nozzle generates no entropy. In any other nozzle, if I had a nozzle with just straight sides like that, I would actually generate some entropy. And I could quantify how efficient it is using that previous equation.